5-volt battery, which you can see on the table as well, where the charge is indicated by the blue light lighting up on the battery. You can see that Mason Bulk uses our test apparatus as consistently as possible for data taking purposes.
And then some applications for the power lifter unit. First would be inside of green gyms. Currently, green gyms are only made up of cardio machines, as depicted on the right-hand side of the screen. The second application would be in large commercial gyms. There was a study done in 2016 by Sports Art that showed that 62.4% of people would rather use environmentally friendly equipment, which directly relates to our project. And then we also had the opportunity to talk to an alumni and founder of Poseidon Strength about our project. He thought it was a great project, but thought it could be translated into constant motion of a bicycle and charging up a backup battery for an electric bike. Here is a video of our unit lighting various light bulbs. The first is going to be a 4-volt, 3-watt LED flashlight. As you can see, the light is lighting both on the concentric and eccentric motion of the lift. The second is going to be a 6-volt, 2.4-watt LED light strip. Once again in the video, you can see it lighting on the way up and on the way down to the lift. And the last is going to be a 12-volt, 4-watt light bulb. The light does light, it's just a little dim. We could show it to you brighter if we integrated a 5-volt to 12-volt converter, but we wanted to show you solely what our unit can power with no extra components.
So going into some of the inner workings of the power lifter, this is a CAD model of what a final manufacturer design will look like. You can see in the highlighted column in the bottom right what the bulb numbers correlate to. Number 1 being the housing base, which houses our pulley and electrical components. Number 2 being the dome cover, which will protect against sweat and dust in the gym environment. Number being our custom-made double sleeve pulley with 5mm diameters to house our cables. Number 5 being our motor cover. Number 6 being the breadboard that houses our circuit. Number 7 being the battery pack we will be charging with this unit. Number 8 being the DC motor. Number 9 being the 4-foot polyurethane belt we use for testing and we use for the unit. And then number 10 being bolts for fixing constant moving around. As for design iterations, we were able to decrease our volumetric footprint from our first semester design by 58%. This allowed for a more sleek design as well as including similar additions to being able to fix the unit to the floor using those side tabs, including a slide for our dome cover to fit over top and additional supports for our motor.
This is the electrical design that we made for this project. It features a brushed DC motor which directs into a diode rectifier bridge, which then runs into the positive side of the 3 millifarad capacitor and into our 5-volt regulator, which then runs into a 11-ohm resistor and our 5-volt battery or light like you saw in the videos before.
Some requirements we set for ourselves for this project. We wanted to be able to power various different lighting apparatuses based on our actual output, just to kind of test and see the limits of it. We also wanted it to be small and modular because this would be sitting on the ground next to the actual cable tower machine. You want to make sure it's a minimal triplet hazard, and then also going alongside that, we want to make sure it doesn't actually impede on the functionality of the cable machine. Because there's lots of heavy weight moving, we want to make sure that it's not affecting that at all, that might hurt the user. And then the main way we actually collect the rotational motion to generate power is by having a double pulley attached to the existing cable equipment that runs down to our ground unit and then spins the motor. And then, as Adam mentioned earlier, we have a way to actually fix the machine to the ground. This keeps it in tension, so we can minimize slip, and then we're looking for a consistent 5-volt output.
So our specifications, we selected the 1N 4005 diodes for our diode rectifier bridge. We considered multiple different diode selections, but these were the most available to us and matched our necessity perfectly. The unit will have generally infinite rotational freedom as long as you're not pulling the cable completely to its limit. But even then, as long as you're not breaking the cable system itself, you're completely fine. We, again, decided on a DC brush motor. We attempted to use a geared head motor as well, but we ran into issues where the torque necessary to actually spin and generate electricity in that case was just too high. So we ended up using a non-gear-based selection. We implemented a 5-volt 3-amp max step-up, step-down regulator into the system, just so that we're not overloading our resistor or any components that we're trying to charge, like the battery and the light. And we also selected a 3 millifarad capacitor, which we'll get into how we test it to determine that.
So as far as the work breakdown structure goes, this semester highly focused on the actual testing aspect here. We stuck with these small all testing, we were looking for what our actual power output was and seeing what the feasibility of that was and what we could do with it. And then we obviously need to make sure our system was robust because it's going to be under constant tension. We want to make sure that doesn't fail and hurt the user at all.
So this is our very general schedule. There's a lot more that went into it, but we want to make it as general as possible. First semester was planning, figuring out what we wanted to do and how we were going to do it. And then second semester was procuring materials to actually try and start getting into testing, making revisions to our design, and then ultimately making a presentation like this.
This is going to be our budget and bill of materials that we use for the first and second semester. On the left-hand side are going to be all the items that we had, and then on the right-hand side is going to be the cost of our group, and then the real-world cost if Wilkes didn't help us with any components or equipment. As you can see, we had $174 total, which is far under the $500 budget.
So that's safety to cover. The two main ones here are holding the safety paramount. Once again, as I mentioned earlier, there's lots of weight moving around in these machines, and you want to make sure that you're not negatively affecting that at all. That could compromise that system. You don't want heavy weight flying around all the users using this. And then another one to focus on was that engineers shall consider the environmental impact and sustainable development in their duties. And this actually directly relates to our project because the whole idea is that we're trying to generate power out of something that is usually just going to waste, and we could reuse that energy.
So this is the general testing setup for the 3 phases of testing we had. First, we have the capacitance testing. On the bottom, you can see a breadboard with a series of capacitors linked in parallel. This is what we use to vary our capacitance easily. And the second is the resistance testing, where we determine the internal resistance of our DC motor generator. And then finally is the power output testing, where we measured our output on the other side of the regulator. I'd also like to mention that all testing was done with the human polling on this. We tried to use a general 1.5 second rep time and then a 30-inch range of motion, and we tried to mimic this as closely as possible for each test. And first, for the capacitance optimization, we initially did some preliminary testing to get us in the ballpark, and we found that to be between 1 and 10 millifarads. Then we tested from 1 through 10 millifarads, looking for the highest peak-to-peak voltage and noise control. And from there, we found our optimal range to be between 2 and 4 millifarads. These graphs are shown from left to right on the bottom of the screen. And through this, we found the 3 millifarad to yield the highest peak-to-peak voltage at 14.9 volts. And for reference, we have the 10 millifarad capacitor test on the top. Even though there isn't a big discrepancy in the noise, the peak-to-peak voltage is a stark difference, as this only yielded 12 volts versus the optimal capacitor with 14.9 volts.
After the capacitance testing, we moved on to resistance optimization. We tested the resistance necessary in 2 different ways. We measured the internal impedance of the DC motor that we were using for our system, which you can see at the top right ended up being somewhere around 12 to 13 ohms. But we wanted to be really sure about this, so we applied that known voltage to the generator and installed the output shaft to measure the amperage, which you can see at the bottom right. Calculating with the stalled current, we measure around 11 ohms, which is what we ended up using for our final circuit. This was really important to us because we wanted to maximize power transfer to our system, minimize energy loss throughout the circuit, and really improve the circuit integrity and protect our components.
Moving on to the actual power output testing that we did. As you can see on the left-hand side, we have the concentric and eccentric motion, which would be the actual pull and return motion that the user would be doing and spinning the motor either way. On the concentric, we have a consistent 5 volts thanks to the regulator and across about 0.8 seconds. And then as far as the return, that goes across about 0.7 seconds, making that 1.5 second repetition time. And it holds the 5 for about half the time and then trickles down to the 3 afterwards. Some things to point out, we actually had still had a power output following the motion, which was an improvement off of our previous prototype. And then also, our actual last semester prototype was about a 1.5 volt average output, so we were able to over triple that. And then due to the regulator's addition, as mentioned, the output was far more consistent, and we even had a generation after the motion. And then some calculated results based on the previous graphs. If you look at the average voltage from the concentric and eccentric motion and the time per repetition, the average amps were obtained by measuring the voltage across the resistor we had And then you're looking at watts generated from one total rep on the concentric mini-centric being about 0.864 watts. And then your typical exercise setup is going to have 3 sets of 10 reps. So we then multiply that output by 30, and then factoring in the time it takes for you to do those 30 reps, you get an output of about 20 watt-seconds per exercise.
And then since there were a lot of, smaller plastic parts in this housing base, we decided it would be best to do a finite element analysis for this to make sure the structural integrity would maintain during tensioning. The no-slip condition required to keep the cable set up would be 7.5 newtons of tension across 2 cables that would equal 15 newtons of force. We decided to simulate with 35 newtons to account for any incidental tensioning in case someone had bumped the cable at any point. And seeing as PLA yield strength is about 40 megapascals, and our bond pieces stress experience was about 17.8, our safety factor was a little bit over 2. We did the same for the tabs and the sides, if those would be fixed to the ground and the base would be experiencing the same tensioning as the pulley. We decided to do a 100 newton distributed load to simulate incidental tensioning and chaotic forces, which would include walking into the unit or someone dropping their phone, etc. The bond pieces stress experienced here was only 1.52 megapascals, which yields a much higher safety factor of about 20.
And then for our lessons learned, first is that interdisciplinary collaboration is really important. I'd like to thank all the EEs that gave us little tidbits on the way. Also, communication needs to be at the forefront of every project. This is something that we definitely struggled with in the first semester, and then we got better at it in the second semester, and we were more cohesive because of it. And then next is a product needs to work one component at a time before it works as a unit. This is something we also struggled with. We just tried to integrate everything together before testing everything individually, and then we really ironed out a procedure to test everything and make sure it's working. And then lastly, the powerlifter has a future, but in a more constant motion application rather than someone using it for 30 seconds and then letting it sit for an hour. And then finally, for some acknowledgements, I'd like to thank our advisor, Dr. Garishi, for pointing us in the right direction, our teacher, Dr. B, for giving us structure, Dr. Zhu for letting us pester him with circuit questions, Suzanne Stash for helping us order all our parts, and then Mitch for helping us tolerance all our 3D printed parts.
You made a statement, charging continues after motion. Could you explain what's causing that and why?
The capacitor before the actual regulator, or at least where I would assume here, is actually charging up and then it's trickling to the regulator. So then even when the regulator outputs a max of 5, and then as the capacitor is able to it's not able to output as much after the motion receives, whatever's left in that capacitor is still going in the regulator, and the regulator is getting out that what it can.
So short answer, it's discharge from the capacitor.
Yes.
Thank you.
Could you go back to your, like the one you're showing the data?
Which one, the capacitance?
Yeah. Okay, so the one you have watts on different watts.
The calculator.
Okay, yeah, right. So at least you see, so why the concentric works a bit better?
So usually on your typical exercise repetition, you're going a bit slower on the way back because you don't want to slam the weights. So that being just a little bit slower spins the motor just a little bit less quickly, and therefore that's why you see that kind of drop off on the way back.
Okay, so during the process, is the capacitor ever fully charged? Did you realize that? Like, does it ever reach the full capacity?
It never capped out, no.
Yeah.
So what I like, you see, for the concentric, you have the consistent 5 volts, right? Like,
Yeah.
For that, so which means that as long as the motion continuous, your charges should be continuous, right?
Yes.
It should be a steady charging process for the battery.
Right.
Okay. So very good. So that's like you see that actually it's a very that shows the voltages regulator actually works pretty well because otherwise your input is just a bunch of spikes. It's really like your input is almost like an impulsive function.
Yeah.
Also
Up to
because
like 10 volts.
yeah, it's a huge like impulse Very good job. Okay.
So do you have any calculations showing how much power you think you could generate, you know, in a normal workout or throughout the day with many people? I don't think it's as bad as you think it is because you're in the realm of watts.
Yeah, so I assume this is, I think it feels a pretty fair average. I showed the total after one completed exercise by one person, but realistically, that your cable equipment is probably going to get used by about 50 people across a whole day. I would say that's, but it's still, yeah, like you're going to see more than just the one exercise worth of power because you're going to have, I would say, like a minimum of 50 uses in your average gyms.
I think even as we were talking earlier this week about it, you could use it as a motivational tactic, right? Like would you be able to constantly light a light bulb as you're going? Okay, I'm going to keep going and I'm going to keep this light bulb lit.
It absolutely is a consideration, especially because the end user at the end of the day is someone who is using the equipment at the gym. And as you can see in our video where we're testing the multiple light apparatuses, some hold that charge for longer. The smaller the voltage and wattage, the longer it's going to stay by our signal that we're putting through. So if you were to do like smaller LEDs as opposed to like your average 12-volt light bulb, you could get that just, you know, almost psychological satisfaction that the end user could experience by keeping that lit during the exercise.
So of all the ones you're showing, which one would be the best to kind of hold the light, give the user enough time to return the motion, and then as long as you went to the normal thing, you could constantly keep that light going?
The best and most realistic would be the first one. However, we actually had a preliminary test in our first semester prototype stage where we were able to light up 4 LEDs consecutively, and so that almost kind of provides like a strength bar, if you want to call it that, which would also be very motivational for the user.
Yeah, like I'm going to try to beat my record.
Keep it at 4 LEDs, yeah.
Okay. I think there's a lot of potential. You know, it's probably not going to be commercialized and put it back in the power grid, but as an individual. We have that one.
Just going to be 15 minutes. All right, so I agree with Mike that you actually included the plots from oscilloscope. So that's a very, you like when you're working on a project, especially as an engineer, your mentality shouldn't be like trying to hide or using, oh, I'm not generating too much power, and that's because anytime when we see like experimental results, especially see a screenshot of a oscilloscope, that makes it trustworthy.
Yes.
So that's, I really appreciate that you had the courage to actually show, seriously, I mean, you see what I mean? Like, it's not about how many watts you are generating. Instead, you are actually trying to show the dynamics. I was very happy to see the consistent 5 volts you were able to generate, which, you see what I mean, makes me feel much better about what you guys are doing. Otherwise, you'd be all laughing. So, but, okay, so one more final, you see, I know this system may be more like even than which is, did you ever try to tune that resistor to, because that resistor controls the charging dynamics. How much do you know about the charging dynamics? Because this is a dynamic process, you see what I mean? Like, just like I was using this, you have a tank, and then there's this in charge of uneven flow, but you want to make sure the outflow is consistent and steady so you can charge your battery, because that's what you need to charge your battery. How much do you understand of the dynamics of charging?
So we did some research beforehand and figured out that we need to match the resistance on the other side of the regulator to the motor. So that's why we did the testing, trying to find the actual resistance and then doing the V versus I stall the motor. So we had 2 different ways of verifying that that was the resistance that we
I
needed.
saw you play with the capacitance a lot, but I didn't see you tune the resistor. Did you ever try to tune that resistor, this resistor in series with the battery? Did you tune? You see what I mean?
Yeah, no, we never.
My experience was that resistor was actually extremely sensitive in terms of how efficient you're doing. Because that resistor basically controls how quickly the charges goes into the battery. So it's depends on, it almost controls the outflow of current.
Yeah.
So if you play with that, I'm not sure if you actually get a chance to play with that, which is almost equally important as this capacitance. So if you play with that, you might get a better charging performance also.
Thank you.
All right, thank you.
Thank you.
Any other questions? Okay, thank you. Great work.